Okay, welcome to ECE 320, Solutions to Homework Set number 4. The first problem is given this max-min circuit. Determine the voltages and currents. I would start with the voltages. I've got these two diodes on the left. Only one of the two can be on. If the first diode, diode A, is on, then the voltage on the right will be 7.7 volts. 7.7 versus 6 is too much, so the second diode turns on. They can't both be turned on. Again, I have two voltages at a node. So let's assume the second diode is on. If this is on, I have 6.7 volts on the right. 6.7 minus a 0.7 volt drop, which is 6 volts. And the first diode is off, so that checks. Diodes on the right. Either the top one or bottom one's on. If the top one is on, it's 5.7 volts, which turns on the bottom. Can't both be on. So assume the bottom one is on. Makes this 4.7 volts. Now in the middle, one of these two is on. If the one on the left is on, then I have 6.7 minus 0.7, 6 volts, and that turns off the right diode. So that works. So those are the voltages, 6.7, 6, and 4.7. Now find the currents. 6 volts across 10K is 0.6 milliamps. 6.7 volts across 1K is 5.3 milliamps coming down. And 12 minus 4.7 over 1K, 7.3 milliamps coming down. The 5.3 milliamps has to go somewhere. Some of it goes right. That's the 0.6 milliamps. The rest goes left to I2. The 7.3 milliamps has to go somewhere. The only diode that's turned on is I6, so that is the current I6, 7.3 milliamps. In Circuit Lab, you can check, build the circuit, and run it. And if you click on the diode on the right side, it'll tell you the current through the diode. The voltages are close. It's comparing them. I calculated 6.7, 6, and 4.7 using ideal diodes. Diodes are not ideal. They're close, but not exactly, so the voltages are slightly off. The currents, likewise, are also close, but a little bit off. That's the advantage of the ideal diode model. I can get answers pretty quickly. If you want to get more accurate answers, throw it in Circuit Lab. Problem 3 is a clipper circuit. Here the trick is draw your straight line approximations to it. The corner on the y-axis is the Zener voltage. I switch. The first Zener turns on at 7.6 volts. The second one turns on at 12.6. The slopes tell you the resistor. The initial slope is 2.533. So that's this circuit. Pick this so that the gain is 2.533. That's 1 plus the resistor ratio. This makes this 1.533 kiloohms. Gives this a gain of 2.533. The first slope is when this Zener turns on. It turns on at 7.6 volts, and then by voltage division, the gain drops. I want to pick it so that the gain, that's the gain in the first stage, times the voltage divider, is 1.67, this slope. Solving, I get R1 is 1925 ohms. Then the last one, when both Zeners turn on, I have these two in parallel. I'll call that R12. Its gain is 0.8, the slope right here. So solving for R12, I get 462 ohms. That's R1 in parallel with R2. I know R1, solve for R2, 607 ohms. So here's your circuit. In Circuit Lab, if I do a sweep, I'm going to sweep V1 from 0 to 10 volts. Look at the output voltage, and that's what you see. Again, notice this is where the first Zener turns on, the second Zener turns on, and that's my approximation for my curve. Problem 5 is design a circuit that clips at plus minus 5 volts. That's actually pretty easy. Just use two Zeners back to back. Each one turns on at 5 volts. Actually 4.3 volts because the Zener has a 0.7 volt drop. When forward biased, it's a diode. 4.3 when reverse biased. Problem 6 is label the regions for a transistor. Again, saturated is when I'm increasing the voltage and I can't quite get enough current. I don't have enough voltage at the collector to power the transistor. That's when I'm saturated. Off is when the current is 0. And active is all the space in the middle. The current gain is the ratio. When the base current is 2.5 milliamps, the collector current is 500. When it's 2 milliamps, it's 400. 1 milliamp is 200. The gain is 200. That's the ratio. We call that beta. That's the textbook I'm using. Other textbooks use HFE. Depends upon your textbook. digit key uses HFE. And the last problem is draw the load line and what happens when Vn is 0, 3, 6, and 9 volts, or 0, 3, 6 volts. So starting out at 0 volts, I have 0 volts, doesn't turn on the diode, and the current is going to be, let's get this picture out of the way. Current is going to be 0, I'm right here. At 3 volts, I have 3 minus 0.7, again this is a silicon diode, voltage drop is 0.7. 3 minus 0.7 over 2K gives you 1.15 milliamps, times 200 gives you 230 milliamps. I'm allowing 230 milliamps to flow. Where that intersects with my load line is my solution. When it's 6 volts, 6 minus 0.7 over 2K is 2.65 milliamps, allowing 530 milliamps to flow. I'm trying to go on this pink line. I can't get there because the orange line can't go past 0. Once you go past 0, it's producing energy, so that's the physical limit. I simply can't go past 0. I can't even quite get to 0. I'll saturate. So the model we use in saturation is it's about 0.2 volts. Close to 0, but not quite. At that point, if VC is 0.2 volts, the remaining voltage across the resistor, and I'll get slightly less than 500 milliamps, 498 milliamps. That's the analysis. If you build it, again, here is my transistor. That's the base resistance. There's the 100 ohms to the collector. Emitter goes to ground. Vary this guy and measure the voltages at the base and the emitter. And here's what I got. Measure the base voltage, collector voltage. I can do that. From that, I can calculate the current. The current is 5 minus 0.77 over 1K, 4.3 milliamps. This is 5 minus 0.045 over 100, 51 milliamps. The ratio is kind of the current gain. I'm actually saturated. I know because this is close to 0. At 10K, again, I'm close to saturated. So this doesn't really mean anything. Once I go into the active region, once VC is bigger than 0.2 and less than 5, I'm active region. In that case, the ratio IB to IC is your gain. Here's 250. Here, this is probably measurement error. I get a gain of 400. The data sheets say between 100 and 300, so this one's kind of suspicious. And when there's no current flow, I get 0 over 0. 0 over 0 is undefined. It's off. What's happening on the load line is at infinity, I'm right here, it's off. 1 meg, 100K, 10K almost saturated. Yeah, maybe it is saturated. 1K is definitely saturated. So that's solution number 4 for ECE 320.